In this video, we're going to take a look at an example that applies the Red Book description of risk assessment, and that would include the steps of hazard identification, dose response, exposure assessment, and risk characterization, to a problem that occurred in food after the Exxon Valdez oil spill some years ago. So we're going to illustrate this risk assessment using the example of the Exxon Valdez oil spill back in March of 1989. After the oil spill, there were a number of native Alaskans who relied on seafood for subsistence living. This was a major source of food for them, and they were concerned that the spill may have contaminated the seafood. So there were people who were already eating the seafood, some people who were waiting for an okay to do that, and the Alaska Oil Spill Task Force requested a cancer risk assessment be done by the Food and Drug Administration in 1990. So this was a real-time risk assessment. By that I mean this was not a research effort. This was something that had to be done quickly with the data that were available. Now there's something else I'd like you to know about this example that I'm going to show you, and that is I'm taking a very narrow piece of what was a very big risk assessment. So they were looking at seal and salmon and all kinds of fin fish and shellfish and everything else. And I'm just going to take bivalve mollusks, and we're going to do an assessment because the numbers are easy to work with and it's easy to understand. But just keep in mind this was part of a much bigger risk assessment. In our risk management class, we've made much about the need to identify problems. And fortunately, back in 1990, the Food and Drug Administration was trying to do this, and they identified the problem this way. There was a need to assess the risk of developing cancer from exposure to polynuclear aromatic hydrocarbons, which we're going to call PAHs from now on, if Alaskan residents consume molluscan bivalves collected from the oil spill area. So this is where, again, I will remind you that they looked at much more than molluscan bivalves, but this is the one we're going to use for our example. So step one in the Red Book risk assessment process is hazard identification, and this is to be done on the basis of the available evidence. And so here is some of the evidence. Here are some of the reasons for considering PAHs. Exposure to them in animal trials showed an increased incidence of cancer in animals. Biodegradation is also a problem. These chemicals are very hydrophobic and they are resistant to microbial degradation, so they stick around for a good while. Then there was bioaccumulation. Mollusks have trouble metabolizing these chemicals, and they don't have the ability to get up and move from polluted areas, so they come in contact with sediments where components of the oil accumulate. And then the final piece for the hazard identification was the simple fact that humans do indeed consume these mollusks. So that's the evidence, a summary of the evidence for the hazard identification step. So let's summarize. PAHs are harmful at low doses. They are the most likely of all the components of crude petroleum to be passed through the marine food chain, and they have been associated with an increased incidence of cancer in animal studies. Therefore, the hazard here is exposure to PAHs. Step 2 was the dose response assessment, and you rarely, if ever, hear that as a component of risk assessment anymore. Even in the food safety world, this step has been redefined as hazard characterization because we've learned that there are many ways to characterize a hazard, not just a dose response. But it's useful for anybody who's going to be working in risk analysis to have at least some passing familiarity with dose response. So let's consider where you get the information for dose response relationships. These could come from animal bioassays, feeding trials. We used to get them from human feeding trials, but that's frowned on now. If you have an outbreak, we might have epidemiologic data. And then more modern approaches include cell lines, where they use tissue cultures to look at the response of cell lines to different doses. But animal studies are most frequently used, so that's what we're going to use for our next slide as an illustration. So you're going to want to watch the animation in this slide as you go through it. Notice that as it begins, we have a vertical axis and a horizontal axis. Dosage is given on the horizontal axis. The response, in this case, an excess tumor rate, is given on the vertical axis. Now, typically what happens when you begin to do some dose response assessment is you would go out to the literature and review it. The literature would give you actual data. They are the 4 circles that you see. Notice that each point in this grid has a dose associated with it and an excess tumor rate. But we only have 4 studies. So what we would do is we would use a statistical technique to fit a curve to those 4 studies. That's the estimated dose response. And by the way, I just drew this all freehand to illustrate the ideas, so please don't take it too literally. Now, because we only had a small sample of 4 studies, we know that if we did 4 studies again, even using the same 4 dosages, we would likely see different responses, different tumor rates. So if we used a different sample, we might expect to have a different estimated dose response curve as well. So we can use classical statistical techniques to develop that upper confidence limit that you see. That is capping the envelope of estimated dose response curves that we could have. So look at that dose response curve that is there and imagine that that was a ½ an inch higher or shifted a little to the right or to the left. That upper confidence limit provides an upper bound on where the actual curve might be. So we use that upper confidence limit as the dose response that we're going to be working with. Notice now that for low dosages, we have no data. We have that one actual data point. It's to the left there, and it's just barely touching the horizontal axis. That's the lowest dose that anybody used in an experimental study. And humans may well be exposed to dosages below that. So what we would like to know is what happens in that low dose range. We've got no data there, and I have drawn for you a linear extrapolation. And that's where we take the origin, the 0, point, and the end of that upper confidence limit, and we just connect them. That relies on an assumption of no threshold, meaning that even one atom of this chemical could cause adverse health effects. And then there are alternative extrapolations from the end of the upper confidence limit to the origin. And so we really don't know what mathematical model fits there. So for the most part, people use a linear extrapolation, and I'll give you an example of that in the next slide. Here's a table taken from a report that indicates how EPA, the Food and Drug Administration, and OSHA handled certain aspects of the dose response curve. Notice the row 3 says preferred cancer low dose extrapolation method if a mathematical model is used. And the simplest here is use a no threshold linear extrapolation method. The point of departure is the data at the upper 95% confidence limit. So that's what you just saw on the previous slide. If you take the time to read what EPA and OSHA do, you'll find out that it's not that much different. So what happened in Alaska? Well, There are many different kinds of PAHs, and there could be many different PAHs present in a single exposure source. What they did is they said, although there are lots of different kinds of PAHs, we're going to compare everything to benzopyrene. So there would be some benzopyrene present, but there would be other chemicals, some that are more potent, some that are less potent than benzopyrene. So they're going to compare everything to benzopyrene's potency. They did a literature review for all cancer bioassays of benzopyrene, and they only found one, a rat study from 1981, and that's what they used. That's what we'll look at next. First, this is not a typical dose-response curve analysis. This was done in real time, so this was quite different, but I've chosen it because it's quite simple. So take a look at the horizontal axis, benzopyrene in milligrams per kilogram daily for a lifetime. Take a look at the vertical axis, the proportion of rats developing tumors. So we have a point here, 0.11 milligrams per kilogram daily lifetime dose of benzopyrene. So with that point, and with the assumption that there is no safe threshold of benzopyrene, meaning even one atom could possibly cause an adverse health effect, we can now take the 0 point and our single point, a ruler and a red pencil, and we can draw the dose response curve that you have there. Then we're going to calculate the slope of this line. It's called a unit risk. It's 1.75, and I'll explain that in the next couple of slides. I do want to give you a caveat here. There was rounding in the study, rounding in the way these numbers have been reproduced. So don't get too worried about the mathematics because there will be some rounding errors that you'll see if you try to reproduce these. Let's quickly review slope. Slope is rise over the run. I just told you there's some rounding error, but I know there are always people who like to check the calculations. So I'm going to show you if you calculate the rise over the run from the numbers shown in that previous slide, you will have 0.18 divided by 0.11, and that gives you a 1.63. So if you allow for the rounding, we're going to use 1.75 as the proportion of tumors per milligram of benzopyrene. So when we talk about a unit risk, we're talking about the unit is 1 milligram of benzopyrene. So 1 milligram of benzopyrene will produce 1.75 tumors. And we're going to say 1.75 what? So let's take a look at that in the next slide. If we interpret a proportion as a percentage, 1.75 means 175%, or 175% of all rats get a tumor. And that doesn't really make sense. And that's because a proportion isn't exactly a percentage. As a ratio, it means we have 175% as many tumors as rats. So on average, 1 milligram of benzopyrene would produce an average of 1.75 tumors per rat. So using the unit risk, the unit is 1 milligram of benzopyrene, and the response is 1.75 tumors per rat. Now we need a little equation so that we can investigate an appropriate level of protection. So I'm using the equation of a straight line, y equals mx plus b. Well, we know what m is. That's the slope, and it's 1.75. We know the intercept. Because we have a no threshold assumption, the intercept is 0. So that makes a very simple equation. Y equals 1.75x. Now what we want to do is we are going to say that we are willing to accept a cancer risk of 1 in a million. So that's 0.00 0.0001 set equal to 1.75x. We solve for x, which would be the dose of benzopyrene that would produce a 1 in a million chance of cancer. So we have an answer here, x equals 5.7 times 10 to the minus 7th. So if you consume more than that amount, now remember we've got a scaling problem here that I haven't addressed yet, so we're going to have to scale that up to a full-sized human being. But if you consume more than this amount, then you have more than a 1 in a million chance of cancer. Again, more than this amount once it's scaled to a human size. If you consume less than this amount, then you have less than a 1 in a million chance of cancer. So this is what it would look like graphically, although it's not very illustrative, is it? On the vertical axis, we have a proportion of rats developing tumors. So we would be looking for 1 in a million chance or 1 in a million additional tumors. And that would be a number way down here near the 0 point. And if we took that number and scooted over to the red line, dropped a perpendicular point down from that, we would get a dose that we were just looking at, which now is 0.57 nanograms per kilogram of body weight every day for a lifetime. So let's summarize our dose response and scale this up to a human. We used 1 point and a no threshold assumption, and we got a 1 in a million lifetime upper bound risk in rats interpolated from the curve at 0.57 nanograms per kilogram daily dose of benzopyrene over a lifetime. They used a 60 kilogram person, which would be a rather small adult in the mainland U.S. today. But if we take a 60 kilogram person, then 0.57 nanograms per kilogram times 60 kilograms says a 34 nanogram daily dose of benzopyrene is an average lifetime dose that will produce 1 chance in a million of contracting a cancer. So if you consume more than 34 nanograms a day, then you have a greater than 1 in a million chance of cancer, and that is considered too risky. If you consume less than 34 nanograms a day, then you have less than a 1 in a million chance, and that would be considered a tolerable level of risk. Step 3 in the risk assessment is the exposure assessment. This is where we figure out how much of the PAH-contaminated food is consumed by Alaskan natives, and we figure out the concentrations of PAHs in those foods. So the average daily intake of bivalve mollusks, according to a survey of Chenega Bay Alaskans, was 2 grams per person per day. That's the mean. 2 grams of a mollusk is about a little fingernail worth, so it's not very much. That is the number that we're going to use going forward, but this is where I need you to recall that this was part of a much bigger risk assessment, okay? This is not the high consumption analysis. We're not looking at the 95th percentile consumer. We're looking at the average consumer. This was a real-time risk assessment. So as part of the exposure assessment, one of the things that the FDA had to do was to figure out the concentration of these chemicals in foods. So we mentioned before there were different kinds of chemicals. Here you see them, benzopyrene, idenopyrene, benzofluorenthine, and they are all expressed as benzopyrene equivalents. So now they went out, harvested some mollusks from the subsistence fishing grounds, and they found that the average level of PAHs was 30 parts per billion of benzopyrene. And if you're not used to working in nanograms per milligram and parts per billion, The units here can get confusing, but don't worry about that. We don't really have to do the conversions ourselves. Here's the lifetime exposure dose calculation. We have found out how much of the chemical would be risky. Now we have to find out how much of the chemical a person is exposed to. So if we use that intake of mollusks, 2 grams per day, and if mollusks have 30 parts per billion of benzopyrene, and we do the multiplication, we end up with a dose of 60 nanograms of benzopyrene per person each day. And that would be the result of the exposure assessment. Now we move to the fourth and final step, the risk characterization. In this case, we're going to compare the actual exposure to the 1 in a million risk. So for a 60 kilogram adult, extrapolating from that animal bioassay data we had, that rat study from 1981, we have less than a 1 in a million risk if less than 34 nanograms per day are consumed. Alaskans are consuming 60 nanograms per day. So if we ask, is this exposure higher than the advisory level? I think we would all agree that 60 is higher than 34. But this was real-time risk assessment. It's science-based. That's not the same as science, so let's have a look. The FDA said prior oil spill data suggests that after 10 years the environment returns to its pre-oil spill status. So they reasoned that people would not be exposed to the presence of PAHs in mollusks for their entire lifetime. So if you assume that exposure to benzopyrene for 10 years of a 70-year lifetime, this is 10 divided by 70, or 0.14, 14% of a lifetime exposure. So 0.14 times 60 nanograms, the lifetime exposure that was estimated previously, we find out, well, it's not 60 nanograms for 70 years. It's only 60 nanograms for some part of 10 years. So if we take that 0.14 times 60, that results in 8.4 nanograms per day as a lifetime dosage. So the exposure in Alaska was judged to be equivalent to an average exposure of 8.4 nanograms per day for a lifetime. So let's restate that. 60 nanograms per day for 10 years was judged to be equivalent to 8.4 nanograms per day for a lifetime. That's not science, folks. That's judgment. And what they concluded was 8.4 nanograms daily for a lifetime is less than the 1 in a million risk of 34 nanograms per lifetime. And so they said it was safe to go ahead and consume the bivalves. So we're going to close out with me reminding you once more that this risk assessment looked at much more than bivalves, and it had a far more complex set of recommendations than I just gave you. But this is the way that you would do a chemical risk assessment in real time using risk assessment as defined by the Red Book.